Imagine, for a moment, the view from far above our galaxy. From this height, the Milky Way spins slowly beneath you, a pale wheel of light turning in a silence so deep it feels like a held breath. Billions of stars drift in their long orbits. Around many of them, unseen from here, small worlds are turning too. Some of those worlds are warm, some are cold, yea, a few perhaps hold something stirring in their oceans or beneath their ice. Between all of these stars, the space is not truly empty. It is filled with a thin haze of dust, with wandering comets, with lost stones flung out of nurseries long ago. These pieces of debris drift for millions of years, sometimes billions. They pass through the dark on paths that no one is watching. And here is the quiet question that opens tonight's long, slow wandering. Could some of those stones be carrying something alive, or the seeds of something alive? Could life, in some form, be moving between the stars, hitching a ride on the broken pieces of old worlds? This idea has a name. It is old, and it is beautiful, and it remains unresolved. Some scientists take it very seriously. Others think it is unlikely. No one can yet say for certain. That is why we are going to sit with it tonight, gently, without needing to answer it. One small thing before we drift further out. The universe has a new wonder for you every single night here. If you'd like one waiting each evening, subscribe and let it find you. Picture a single grain of rock, no bigger than a pebble. It was thrown from the surface of some distant planet 100 million years ago. Perhaps an asteroid struck that planet, and the force of the impact sent shards of crust flying upward, faster than the planet's gravity could hold them. Some of those shards fell back. A few, the lucky ones, kept going. They passed the edge of the atmosphere. They passed the moons. They slipped into the long night between the stars. If anything living was tucked inside that pebble, a spore, a sleeping microbe, a chain of stubborn molecules, what would happen to it out there? Would it die in the cold? Would radiation break it apart? Or could it sleep, dry and still, for eons, waiting? And if such a pebble ever fell, at last, into the warm sea of another world, would that sleeping traveler wake? This is the puzzle we call Panspermia, the idea that life may spread between worlds. In its gentler forms, it suggests only that ejected rocks from Mars or Earth could pass small living cargo between neighboring planets. In its bolder forms, it suggests that life on Earth itself may have arrived here from somewhere else. And in its wildest forms, it suggests that the whole galaxy might be quietly connected, one biosphere seeding another across unimaginable time. None of these ideas is proven. All of them are being studied. Each one has thoughtful defenders and thoughtful critics. Some researchers point to how quickly life seems to have appeared on the young Earth and wonder if it had help. Others point out that we simply do not yet know how life begins, and so we have no good way to measure whether it needs help at all. The evidence is thin, the imagination is wide, the question is open. Tonight we will drift through this old idea slowly. We will visit the meteorites that have already fallen to Earth, carrying strange chemistry inside them. We will meet the tiny creatures that shrug off radiation and vacuum. Still living after trips to orbit, we will look at the interstellar visitors that have passed through our own solar system in recent years, silent tourists from somewhere else. We will consider the possibility that comets carry the raw ingredients of biology, and the further possibility that they carry something more. We will not resolve the mystery. We are not here to. We are here to let the mind soften around a very old question, one that human beings have asked in different words for thousands of years. Are we alone? And if we are not alone, are we connected? Is life something each world invents for itself, again and again, or is it something that travels, patient and quiet, from one warm place to the next? Settle in. There is no hurry. The stones are still drifting out there, slower than thought, older than memory, and for the next few hours we will drift with them, gently, through the dark, wondering what they might be carrying, and where in time they might be going. The word itself is old, older than most of the sciences that now try to test it. Panspermia. It comes from two simple Greek roots, pan meaning all, sperma meaning seed. Put them together and you have a phrase that means, roughly, seeds everywhere. Seeds scattered across all of space. The idea is exactly as gentle and as strange as it sounds. Life, in this picture, is not something that begins fresh on each new world. It is something that drifts, something that travels, something that arrives. At its core, panspermia is the notion that living things, or the raw chemical starts of living things, can move from one place to another through space, from a moon to a planet, from a planet to another planet, from one star system to a second, one many light years away. The size of the traveler in this idea is very small. We are not talking about creatures with eyes or bones or leaves. We are talking about microbes, tiny single cells, so small that 1 million of them could rest on the head of a pin without crowding one another. If life rides the stars, it rides in packages we cannot see with the naked eye. The vehicles in this idea are simple too: rocks, dust, chunks of ice, fragments of frozen comet, bits of shattered crust flung off a world by the force of a large impact. Imagine an asteroid striking a planet with enough energy to throw pieces of the ground upward, faster than the planet's gravity can hold them. Some of those pieces would climb past the sky and keep going. They would fall into long, slow orbits around the local star, A. Very small number of them, over very long times, might drift out further still, past the edge of the star's pool, into the deeper dark between suns. The distances involved are hard for a human mind to hold. Between Earth and Mars, the gap can shrink to about 50 million kilometers when the two planets pass close. That already sounds enormous. A jet plane, flying without stopping, would need more than 6 years to cross it. Yet the gap between our sun and the nearest other star is nearly 1 million times greater. A rock, coasting quietly at the speeds we usually see for ejected debris, would need many hundreds of thousands of years to cross that distance. Some models suggest journeys of millions of years. In panspermia, patience is not a virtue. Patience is the whole premise, the ages involved, stretched just as wide. Our solar system is about 4.5 billion years old. Life on Earth appears in the rock record surprisingly early, within the first billion years, and possibly much sooner than that. If seeds truly do drift between stars, they have had 10 billion years or more of galactic history to do it. That is more than twice the age of our own sun. Long before Earth existed, older stars had already lived, died, and scattered their planet's debris into the wider galaxy. The composition of the seeds in the softer versions of this idea need not be full living cells at all. Some researchers speak of molecular panspermia. In this gentler version, what travels is not a microbe, but the ingredients, amino acids, sugars, the small carbon-based building blocks that life on Earth uses. These have already been found in meteorites and in the dust of comets. Whether that counts as panspermia in the strict sense is itself an open question. Some scientists call it partial delivery. Others say it is only chemistry, not biology. And the leap from ingredients to living cells still has to happen locally, on each world. There are stronger versions of the idea and weaker ones. Lithopanspermia, the transport of microbes inside rocks, is the version most often studied in labs today. Interstellar panspermia, the crossing of the great gulf between stars, is a bolder claim and much harder to test. Directed panspermia, the notion that some intelligence long ago deliberately sent life outward, is the most speculative branch of all, and most researchers treat it as a thought experiment rather than a working hypothesis. The competing view held by many is simpler. Life arose here from local chemistry on its own. No delivery required, no cosmic postage. So the basic picture is this: very small living things, or the chemicals that lead to them, riding on very small rocks across very great distances over very long times. Whether any of this actually happens in our galaxy, whether it has ever happened, whether it happened to us, remains unknown. That, in the simplest terms, is what panspermia really means. A quiet, unproven possibility that the universe passes seeds from world to world in the dark. To understand how a rock could ever leave one world and drift toward another, we have to picture the moment of its birth. And that moment, almost always, begins with a collision. Somewhere in the deep past of a planet's history, a smaller body comes falling in from the dark. It might be a stray asteroid, a fragment of an old comet, or a chunk of debris left over from the making of the solar system. It arrives at tremendous speed, moving faster than any rifle bullet, faster than most things you can easily picture. When it strikes, the ground does not simply crack, it behaves. For a brief instant, almost like a fluid, shock waves ripple outward through the crust. Rock melts, rock vaporizes, a crater opens like a slow bloom, and along the very edges of that violent flowering, a strange thing happens. Not everything is pulverized. Some slabs near the rim are lifted and hurled upward at just the right angle, just the right speed to keep going. They do not fall back. They rise past the clouds, past the thin blue veil of the atmosphere, and out into the black. For a rock to escape a world entirely, it must reach what scientists call escape velocity, the speed at which a moving object breaks free of a planet's gravity for good. On Earth, that speed is around 11 kilometers per second. On Mars, with its weaker pull, the number is closer to 5. That difference matters more than it might sound. A smaller world with less gravity is far easier to leave. Every impact on Mars over billions of years has been quietly launching material into space, some of which drifts our way. Every impact on Earth has done the same, though our thicker atmosphere and heavier gravity make it a rarer event. The physics of this launch is surprisingly gentle for a small fraction of the material involved. Near the outer edge of an impact zone, some rocks are accelerated by the shock wave rather than crushed by it. They get a hard shove without being shattered. Studies of Martian meteorites found on Earth suggest that certain minerals inside them never exceeded temperatures that would sterilize the stone through and through. The core of such a rock, tucked inside a thick shell of protective material, might stay cool enough that anything living in its cracks could, in principle, survive the ride out. This is where the story becomes an open question rather than a settled one. We know rocks escape planets. We have the meteorites in our hands to prove it. What we do not know is how often the interior of such a rock stays hospitable during the launch itself. One view holds that most ejected material is heated and shocked so severely that no microbe could possibly live through it. A competing view suggests that a meaningful fraction of ejected stones preserve cool, shielded pockets deep inside. The truth may lie somewhere between. and it may vary from impact to impact, world to world. Even the shape of a launch matters. A glancing blow at a shallow angle can loft material with less shock than a direct vertical strike. Some researchers wonder whether certain kinds of impacts are far better at seeding space than others, and whether the history of a planet's cratering record might, in a hidden way, tell us how often it has been sending pieces of itself outward. Once a rock is free, it enters a very long story. It might loop around its parent star for millions of years, occasionally crossing the paths of other worlds. It might be nudged by the gravity of a passing planet and thrown onto a wider orbit. In rare cases, over immense stretches of time, some of these stones can be flung out of their solar system entirely, cast into the space between stars. Whether they carry anything more than minerals is the deeper question this whole episode circles around. There is a quiet beauty to it. If you sit with the image, every crater on every moon and planet you have ever seen a photograph of represents an ancient launch pad. Somewhere out there, drifting slowly through the cold, are the scattered pieces of worlds long since changed by erosion or geology. Some of those pieces came from Mars, some came from our own moon, a few perhaps came from farther still, from worlds whose names we will never know. Whether any of them carried living passengers is the mystery. The launch, at least, we can be sure of. The rocks do leave. They have been leaving for billions of years. What rides inside them, and whether anything inside them ever wakes again, remains one of the softest and most patient questions in all of science. Before a stone can carry life between stars, it must first survive the long silence between them. That silence is not empty. It is thin, colder than almost anywhere you can imagine, and stitched together by faint threads of matter and light. To picture what a traveling rock is made of, and what it passes through, we have to think about where all these ingredients came from in the first place. Every atom in a wandering stone has a history. The silicon in its grains, the iron in its veins, the tiny flecks of nickel and magnesium and sulfur. All of them were forged inside stars that lived and died long before our sun was born. Massive stars burned through their fuel, made heavier and heavier elements in their hot cores, and then scattered those elements into space when they collapsed. The clouds left behind slowly cooled, gathered, and gave rise to new suns and new worlds. So, a rock drifting between star systems is, in a real sense, a small piece of an older star still traveling. The minerals that make up such a rock are the same ones we know from Earth and from the meteorites that fall here. Olivine, a pale green crystal that also lines parts of our planet's mantle. Pyroxene, dark and glassy. Feldspar, which gives many stones their milky sheen. Tiny grains of metal, sometimes pure iron, tucked into the stone like seeds in bread. Some meteorites also carry carbon-rich patches, dark and soot-like, holding organic compounds, molecules built around carbon, the same element that anchors every living thing we know. Water may be there too, locked inside the minerals rather than sloshing free. Certain clays and hydrated crystals hold water molecules within their structure, releasing them only when heated. When comets and asteroids strike a young planet, that bound water can flood out and pool. Many researchers think much of Earth's ocean arrived this way, delivered slowly by icy visitors during the chaotic early years of the solar system. Whether comets or asteroids brought more of it remains an open question, and the answer keeps shifting as new data comes in. The organic molecules found inside some meteorites are especially interesting. Sugars, amino acids, and pieces of the compounds that form the rungs of DNA have all turned up in space rocks that fell to Earth. These are not living things. They are only the raw pieces. But the fact that such pieces already exist inside cold stones drifting through the dark tells us that the chemistry of life is not confined to warm planets. Some of it is baked into the universe itself, born in the dust between stars. That dust is the other half of the story. The space between suns is not truly empty. It is threaded with a fine haze of grains, each smaller than a wisp of smoke, along with hydrogen gas, helium, and traces of heavier elements. In some regions, this haze thickens into vast dark clouds where new stars are being made. In others, it is so thin that a single grain might sit alone in a cubic kilometer of vacuum. A rock passing through would meet these grains only rarely, brushing against the ghost of a former star. Cosmic rays weave through this thin medium. Fast-moving particles flung out by exploding stars and other violent events far away. They stream in every direction, quiet and invisible, and they carry enough energy to break apart molecules over long periods. A stone, drifting for millions of years, would slowly accumulate their damage, its outer layers chipped at atom by atom. Whether anything tucked deep inside could ride out that steady rain is one of the big unresolved questions of panspermia, and later sections will sit with it more closely. For now, hold the picture in mind. A stone in interstellar space is a small, compressed history of the galaxy. It carries iron born in a supernova, silicates cooled from an old nebula, carbon left over from ancient stars, and perhaps a few water molecules bound tight into its clay. It moves through a hush of hydrogen, so thin it can barely be called a gas, past the occasional dust grain, under a soft, constant hail of radiation from distant catastrophes. Everything about it is connected to everything else. The elements in the rock, the chemistry inside your own body, the ocean on Earth, the clouds, where new stars are gathering right now, hundreds of light years away. Whether life itself can survive that long silence between worlds is still unknown. What is clear is that the ingredients travel freely, drifting in the dark, tying every planet and every star to every other one in a slow, quiet exchange that has been going on since the galaxy was young. Every year, small stones fall from the sky. Most burn up before they reach the ground. Few survive the fiery passage and land quietly in fields, on rooftops, on frozen lakes, in deserts where the sun bleaches them slowly over centuries. These are meteorites. They are the postcards of the solar system, and each one has a story pressed into its atoms. The forces that carry a meteorite to Earth are older and stranger than they first appear. It begins with gravity, the gentle, patient pull that holds every world together and shapes every orbit. Gravity is what tugs a wandering rock toward our planet across the long dark. It is also what once threw that rock away from its home. Somewhere, long ago, a bigger body was struck. Gravity gathered the debris. Gravity sent it drifting. Gravity now delivers it to a farmer's field. Between those two moments, the rock lived a quiet life under other forces. Cosmic rays, which are tiny particles moving almost as fast as light, rained on its surface for millions of years. When these particles strike a stone, they leave subtle chemical fingerprints. Scientists can read those fingerprints and estimate how long the rock traveled through open space. Some meteorites carry marks suggesting they drifted for tens of millions of years before finding us. Others show only a brief flight of a few million. The wandering times are wildly different, and that alone hints at how varied the paths through the solar system can be. Heat also shapes these travelers, but in a peculiar way. Deep space is cold, close to the coldness of empty vacuum, A stone tumbling through it holds no warmth except what starlight brushes onto its surface. So the interior of a meteorite spends millions of years at temperatures far below freezing. If anything lived inside, it would not grow or breathe. It would simply wait. This deep cold may be one of the great protective forces of the Panspermia idea. Cold slows chemistry. Cold pauses damage. Cold preserves. Then comes the fire. When a meteorite meets Earth's atmosphere, it slams into a wall of air, moving thousands of miles per hour. The outer surface glows white, then peels away in glowing flakes. This burning layer is called the fusion crust. It is thin, sometimes only a few millimeters beneath it. The interior of the stone can remain surprisingly cool. Researchers have measured meteorite interiors that were still cold to the touch, minutes after landing. Some samples were even coated in frost. This gap between the outer inferno and the inner chill is one of the strangest details in the whole story. It is the reason some scientists wonder whether a fragile passenger, tucked deep inside, could ride through that fire and live. Pressure plays its part too. The impact that ejects a rock from a planet must be violent, yet not too violent. Studies of shock physics suggest that certain zones near the edge of an impact can launch material at speeds high enough to escape a world's gravity, while the rock itself experiences pressures its minerals can survive. This is called the spallation zone. It sits at the outer edge of the crater's fury. If a stone happens to sit there when a large asteroid strikes, it can be flung upward almost intact. Whether tiny living passengers could endure that squeeze remains an open question. Some laboratory experiments suggest hardy microbes might survive such shocks. Others suggest the pressures would tear cells apart. The evidence pulls in both directions. Magnetism weaves through the tail as well. Some meteorites carry weak magnetic signatures frozen into their minerals when they cooled long ago. These faint traces let researchers guess at the magnetic fields of the ancient bodies the rocks came from. That, in turn, hints at whether those bodies once had warm interiors, molten cores, perhaps even liquid water. A rock that formed on a wet, warm world is a very different candidate for carrying life than one that formed on a dry, cold pebble. Every meteorite is a small experiment in survival. It has been thrown, cooked, chilled, radiated, shocked, and finally slammed into our sky. That any of them arrive intact is remarkable. That some contain organic molecules, the simple carbon-based building blocks of biology, is more remarkable still. Whether they ever carried anything alive is a question no one has answered. For tonight, picture a single stone drifting between worlds, its outer skin dark with age, its interior cold and quiet, the forces of the universe pressing on it from every side, yet somehow leaving its heart untouched. Sleep on that image, the traveling stone, the patient dark, the unanswered. Somewhere on Earth tonight, sitting in a museum drawer or a laboratory freezer, there are small dark stones that did not come from here. They came from Mars. We have found about 300 of them so far, scattered across places like Antarctica, the deserts of North Africa, and the dry hills of Australia. They are quiet little travelers, some no bigger than a walnut, some the size of a grapefruit, and each one holds a story we are still trying to read. To feel the scale of their voyage, picture two small towns on opposite sides of a wide valley. Mars is one town, Earth is the other. The valley between them, at its narrowest, is about 34 million miles. At its widest, when the two planets sit on opposite sides of the Sun, the gap swells to more than 250 million miles. Now imagine tossing a pebble across that valley with nothing but the force of an ancient impact. That is what these rocks did. The launch itself must have been staggering. When a large asteroid slammed into the surface of Mars millions of years ago, the shock lifted chunks of crust faster than the planet's own gravity could hold them. Mars needs an escape speed of about 5 kilometers per second. That is roughly 11,000 miles per hour, or about 15 times the speed of a passenger jet. The stones that made it were the ones flung upward at just the right angle, at just the right speed, from just the right spot near the impact. Once free, they drifted for a long time. Some of the Martian meteorites we hold in our hands today spent between 1 million and 15 million years floating between the two worlds. Think about that stretch of time. 15 million years ago, the first ancestors of the great apes were only beginning to appear on Earth. The rock was already in space, tumbling slowly, catching sunlight on one side and losing heat to the void on the other, waiting. The size of these travelers helps put the puzzle in scale. Most Martian meteorites weigh less than a pound. A few weigh several pounds. The largest ever found, a stone called Tau Deni 002, is about 14 kilograms, or roughly the weight of a small dog. That is not much material. And yet, if you gathered all the Martian rock we have ever recovered on Earth, it would still fit comfortably inside a single kitchen refrigerator. From an entire neighboring planet, across billions of years, this is our whole sample. Scientists estimate that many tons of Martian material still fall to Earth every year, most of it unnoticed, most of it small as sand grains, over the 4.5 billion year history of our planet. That adds up. Some researchers wonder whether hundreds of millions of tons of Martian rock have quietly arrived here, buried now in ocean sediment, or lost to weather. If any of it once carried living microbes, those microbes had a chance to land on a warm, wet, welcoming world. The reverse trip is harder. Earth's escape speed is more than twice that of Mars, about 11 kilometers per second. It takes a much bigger impact to launch our rocks outward. Still, some models suggest that Earth material has almost certainly reached Mars at least a few times in the long history of the solar system. Whether it arrived alive is another matter, and that question remains open. The temperatures involved are gentle in one sense, and cruel in another. Deep space, far from any star, sits at about minus 270 degrees Celsius, only a few degrees above absolute zero. Inside a rock, traveling through that cold, the interior stays, only slightly warmer, protected a little by the mineral shell around it. There is no water, no air, no food, no sunlight reaching the middle of the stone, just cold, and time, and the slow drift of momentum. Then comes the arrival. A rock entering Earth's atmosphere hits the outer air at speeds between 11 and 70 kilometers per second. The outside of the stone can reach temperatures hotter than the surface of a light bulb filament, glowing white for a few seconds before it slows. And yet the inside, just a few centimeters deep, often stays cool enough that a fingerprint of the original mineral remains untouched. That is the strange promise of these Martian stones. They prove that natural delivery between planets is not a fantasy. It happens. It has happened many times. Whether any of them ever carried a passenger, awake or asleep, is a question we are still learning how to ask. The stones themselves are quiet. They are not telling us yet. Picture, for a moment, that you could shrink down small enough to walk across the surface of a single grain of rock tumbling through space. The stone beneath your feet would look nothing like the smooth pebbles of a riverbed. It would be pitted and cratered on a tiny scale, full of shadowed pockets, rough ridges, glassy patches where old heat once melted the minerals. Dust would cling to every crevice, and somewhere in those hidden pores, if the more curious theories of Panspermia are correct, something might still be alive. That something would be very small, smaller than a speck, smaller than the smallest thing your eye can see, a microbe, perhaps only a few thousandths of a millimeter across, curled into itself like a seed. If you could magnify it, you might see a rounded shape with a thick, leathery outer wall. Not glossy, not soft, more like a tiny stone within a stone. Inside, its water would be almost gone. Its chemistry would be paused. It would look, for all purposes, dead. And yet, some microbes on Earth can wake from this state after astonishing lengths of time. Scientists have revived bacteria pulled from deep salt deposits, from ancient ice, from the guts of long-buried insects trapped in tree sap. Each recovery has raised the same quiet question: if life on our planet can pause itself so completely, could it also survive the long, cold silence between the stars? One organism keeps returning in these discussions. Its name is Deinococcus radiodurans, and it is a small pinkish bacterium that clumps together in groups of 4 under a microscope. Its colonies look almost cheerful, soft, pale, rose-colored patches on a laboratory plate. But this modest little creature can shrug off radiation doses that would kill almost anything else, doses hundreds of times stronger than what would end a human life. It repairs its own broken genetic material with startling speed, stitching itself back together as fast as the damage arrives. Nobody is entirely sure why. One idea is that it evolved this power on Earth, adapting to survive long droughts when its DNA would break simply from drying out. Another possibility, floated by a few researchers, is that such extreme resistance hints at a history of surviving conditions harsher than anything on our planet's surface. That second idea remains speculative. The evidence for it is thin, and the drought explanation may be enough. The question sits open. Then there is the tardigrade, a tiny 8-legged creature sometimes called a water bear. If you could see one at its full, unimpressive size, it would look like a plump little pillow with stubby legs no bigger than a grain of salt. Under strain, it can pull in its limbs, expel its water, and shrink into a hardened barrel-shaped form called a tum. In this state, tardigrades have survived direct exposure to the vacuum of space, at least for short periods. During low Earth orbit experiments, they have also endured deep cold, crushing pressure, and radiation levels that should have destroyed them. Whether any Earth organism could truly survive millions of years drifting between stars, however, is a very different question. Short exposures on a space station are one thing. The vast, slow, quiet crossing between solar systems is something else entirely. Some researchers think the outer layer of a rock could shield a microbe long enough for a hop between neighboring planets, perhaps from Mars to Earth, in only a few million years or less. Others argue that cosmic rays would gradually shred any DNA over such timescales. No matter how deep the microbe hid, both sides can point to real experiments. Neither can claim the final word. If you kept walking across that imagined rock surface, you might pass over a patch of dark carbon-rich material, then a lighter vein of silicate mineral, then a hollow where ice once sat before boiling away into the void. Every texture matters to the question. A porous stone hides more microbes than a smooth one. A darker stone absorbs more heat during a fiery launch and might sterilize its passengers. A stone, rich in clays, might hold water molecules bound tightly in its structure, offering a little chemical company to any traveler curled inside. The surface of a wandering rock is, in this sense, both a landscape and a laboratory. Every ridge and shadow becomes a possible shelter or a possible tomb. We do not yet know which is more common. We do not know whether any earth microbe has ever ridden such a stone across the darkness and lived to wake on the other side. The stones keep their secrets, and the little sleepers, if there are any, keep sleeping. Beneath the crust of a rocky world, life has a quiet trick. It goes to sleep. Certain microbes, when the world turns cold or dry or hungry, fold themselves into thick shells and simply stop. They stop eating. They stop growing. They stop, in most measurable ways, being alive at all. And yet, when conditions warm again, they wake. This ability to sleep, to pause life without ending it, sits close to the heart of our question tonight. The scientific name for this deep sleep is dormancy. A bacterial spore is a small, tough capsule wrapped around the essentials of a cell. Inside, the water is nearly gone. The chemistry has slowed to a whisper. The outer coat is layered and hard, built to shrug off heat, cold, acid, and dryness. In this state, a spore is not really doing anything. It is only waiting. The waiting can be very long. On Earth, researchers have found bacterial spores tucked inside ancient salt crystals and deep in old sediments, and some appear to have stayed viable for many thousands of years. A few contested studies have suggested even longer sleeps, reaching back millions of years, though these results remain debated. The truth is, we do not know the true upper limit. Life, once it has curled itself up small enough, may be able to wait far longer than we can easily test. This matters for the question of traveling life. A trip between stars is not measured in years or centuries or even in thousands of years. It is measured in millions. So any microbe hoping to cross that gap would need to be very, very good at waiting. A spore inside a rock, buried a few meters deep, cold and dark and still, is one of the few forms of life we can even imagine surviving such a journey. Not living through it, exactly. Sleeping through it. Frozen seeds work in a similar way, though for a different kind of life. Plant seeds bury their code inside a hard shell, drop the water out, and go still. In the right conditions, cold, dry, undisturbed, some seeds have sprouted after thousands of years. It is a plant world echo of the same trick the microbes use. Life has learned, again and again, that the way to survive impossible waits is to stop being active life at all, and to become something more like a message in a bottle. Yet even sleep has limits. Inside a dormant spore, slow damage still accumulates. Cosmic rays, which are tiny particles moving at nearly the speed of light, can pierce rock and cell walls alike. Each strike can break a small piece of the microbe's genetic code. Given enough time, the code becomes unreadable. The waiting body forgets how to wake up. So the real question is not whether spores can sleep, but how deep inside a rock they would need to be, and how long the trip could last before the damage overwhelms them. Some researchers argue the shielding does not have to be very thick. A meter or two of rock, they suggest, could block enough radiation to protect a small pocket of dormant cells for a very long time. Others are less hopeful. They point out that over millions of years, even faint background radiation adds up, and that the delicate machinery inside a cell is easier to break than to preserve. In their view, interstellar journeys would sterilize almost any rock long before it reached another star. Both views draw on real data, and both remain incomplete. We have never actually watched a spore sleep for 1 million years. We can only run experiments for a few decades at most, and try to extrapolate from there. The gap between what we can measure and what we need to know is enormous. There is also the question of what wakes them. A dormant spore does not decide to open. It responds to warmth, water, and nutrients. So even a perfectly preserved sleeping cell, riding inside a rock, would need to arrive somewhere gentle. It would need to be broken loose from its shell, landed on a wet and warm world, and given the right chemistry to stir. Any one of those steps failing means the sleep simply continues, quietly, forever. Picture it, for a moment, deep inside a dark stone. Drifting between suns, a single curled cell holds all the instructions for a form of life. It does not know it is traveling. It does not know how long it has been asleep. It only holds and waits and holds. Whether such travelers ever really cross the gulf between stars, we cannot yet say. The sleepers, if they exist, are keeping their secret well. Picture a small stone drifting through the deep dark between stars. It tumbles slowly, end over end, catching only the faintest glimmer of distant suns inside its cold heart. If life is there at all, it sleeps in silence. Around it, the vacuum hums with radiation, with particles born in ancient stellar deaths, with the slow drizzle of cosmic rays that have crossed the galaxy. The stone itself is the whole story. Without it, any living thing on the surface would be gone in minutes. With it, the possibilities open up in ways we are still trying to measure. A rock is a shield, and a shield changes everything. Cosmic rays are tiny bullets moving near the speed of light. They come from exploding stars, from the churning cores of galaxies, from sources we still cannot fully name. When they strike a naked cell, they snap the delicate threads of its genetic code. A single hit can be repaired. A steady rain over millions of years cannot. So, the question becomes simple. How much rock does a sleeping microbe need above its head to stay safe long enough to reach another world? The answer depends on which kind of radiation you fear most and how long the trip takes. Studies of meteorites suggest that even a meter or two of stone can block a large share of the harmful particles. A boulder, several meters across, might protect its deepest interior for millions of years. A stone the size of a small hill might shelter its core for far longer than that. Nobody knows the exact number because the conditions vary with every path through the galaxy. The rhythm of protection has its own quiet cycle. Radiation strikes the outer skin of the rock, breaking it down, molecule by molecule, bit by bit. The shield thins. Meanwhile, tiny impacts from dust grains chip the surface away. Over long stretches of time, a traveling stone loses its outer layers like an onion shedding paper. If it starts too small, it may erode down to nothing before it arrives anywhere useful. If it starts large enough, its inner heart remains fresh, even as the outside is scoured raw. There is a strange elegance in this slow erosion. The rock protects the life inside by sacrificing itself, layer after layer, over ages. It is a kind of slow burn without fire, a candle whose flame is time itself. And within that shrinking shell, if a spore is truly there, it waits. It does not age the way we age. It simply sits inside a chemistry that has almost stopped. Some researchers wonder whether certain minerals inside the rock might do more than block radiation. Iron-rich grains, salts, even trapped ice could absorb harmful particles or repair small chemical damage over time. One idea is that the interior of a rocky fragment could act almost like a natural cold storage vault, with mineral chemistry buffering the fragile molecules of life against slow decay. Another view is less hopeful. Even inside a shielded core, the natural radioactivity of the rock itself keeps ticking. Uranium and thorium and potassium releasing their own quiet stream of particles. That inner radiation cannot be shielded away. It rises from within, so there is a tension baked into the physics. The rock protects life from the outside universe, but its own atoms betray it from within. Which effect wins in the long run is not fully settled. Laboratory work on bacterial spores gives hints, not certainty. Some spores seem to survive doses far beyond what anyone expected. Others fail sooner than the models predicted. The truth is that we have never watched a rock cross between stars. We have only tested tiny pieces of the problem in short experiments close to home. The cycle of protection also depends on what the rock is doing along the way. A stone that spirals near a hot young star will bake. A stone that grazes a dense cloud of dust will erode. A stone that passes through the empty spaces between spiral arms may travel for ages almost untouched. Each path writes a different fate for the sleeping cargo inside, and so the shield of a thick rock is not a single answer, but a long conversation between stone and space. It works in theory for certain sizes and certain distances and certain kinds of life. It fails in theory for others, somewhere in the balance between shield and radiation, between erosion and endurance, between inner glow and outer bombardment. The possibility of interstellar life either lives or dies. For tonight, that balance remains open, still turning slowly in the dark. Imagine a single grain of rock, no larger than a pea, drifting between the stars. It left its home world in a blazing impact millions of years ago. Now it coasts through the empty spaces of the galaxy, spinning slowly, catching starlight on one face and darkness on the other. Around it lies the neighborhood of deep space, and that neighborhood is unkind to living things. The first neighbor is radiation. Space is filled with tiny particles moving at almost the speed of light. Some come from the sun, others come from distant stars that exploded long ago. These particles are called cosmic rays, and they pass through matter like bullets through paper. When one strikes a cell, it can break the delicate strands of DNA inside. A living thing exposed to open space would take countless hits over the years. Each hit damages the code that keeps the cell alive. Some tiny creatures on Earth can repair this damage. A bacterium called Deinococcus radiodurans is famous for stitching its shattered DNA back together after huge doses of radiation. In laboratory tests, it has survived exposures that would kill almost anything else. Researchers have wondered whether such a creature could endure the long crossing between stars. The answer depends on how deep inside a rock it hides. Near the surface, the radiation would slowly wear it down, deep within a boulder. Buried under many feet of stone, the same creature might be shielded well enough to sleep for ages. The second neighbor is the vacuum. Space has no air, no pressure, no moisture on Earth. We think of a hard vacuum as a hostile place. Yet many microbes handle it better than you might expect. Some dry themselves out into a kind of glassy state, drawing every drop of water out of their tissues. In this state, called anhydrobiosis, they do not really live, and they do not really die. They simply wait. Tardigrades, the tiny 8-legged creatures often called water bears, can enter this state and survive being placed in open space for days at a time. Experiments carried out on the outside of orbiting laboratories have shown that some tardigrades return to life after the trip. Whether they could last centuries or millennia in the same condition is still unknown. Then there is the cold. Between the stars, temperatures fall close to the lowest possible reading, only a few degrees above absolute zero. At such cold, chemistry almost stops. Water becomes hard as steel, fats and proteins stiffen. Any process we would call life grinds to a halt. Yet this pause may be a gift rather than a threat. A frozen microbe uses no energy, produces no waste, and ages far more slowly than one at room temperature. Some researchers think the cold could be the very thing that makes long journeys possible. Others argue that even in deep freeze, damage from radiation keeps building up, one broken bond at a time. Until nothing living remains, the neighbors do not act alone. They work together, sometimes helping the traveler, sometimes harming it. A thick rock shields against radiation, but also traps heat from radioactive minerals inside. That warmth might keep a small pocket of water liquid for a while, giving hidden microbes a place to rest. On the other hand, the same warmth could speed up the slow decay of their molecules. The balance between shielding and slow ruin is one of the great puzzles of this whole idea. Scientists have tried to model the odds. Some studies suggest that a rock a few feet across, launched from Mars, could carry protected microbes to Earth in as little as a few years, well within the survival limits of hardy species. Trips between star systems are a different matter. Those journeys stretch across millions of years. During that time, even the best shielded spore might slowly lose the ability to wake up. One team of researchers has calculated that after 10 million years in interstellar space, only a tiny fraction of any starting population could still be alive. Another team argues the number could be higher if the rock is large enough. The models disagree because the inputs are uncertain. And the inputs are uncertain because no one has ever tested a real interstellar traveler in the laboratory. For now, the neighborhood of deep space remains a place we understand only in pieces. We know it is cold, empty and bathed in slow radiation. We know some life on Earth can survive parts of it. What we do not know is whether any living thing could survive all of it for long enough, in the right kind of shelter, to cross the gulf between suns. The rock keeps drifting. The question keeps turning with it. Suppose a stone has done the impossible. It has been thrown from its homeworld by a great impact. It has drifted through the deep cold and dark for thousands, maybe millions of years. Its passengers, if they exist, have slept the whole way, and now, at last, the stone falls toward a new world. It meets an atmosphere, and in a matter of seconds, everything changes. This is the last great test, the fiery return. A meteor, entering an atmosphere like Earth's, slams into the upper air at speeds that can reach 40 or 50 kilometers per second. That is more than 100 times faster than a rifle bullet. The air in front of the rock has no time to move aside. It compresses, it heats, it glows. The surface of the stone can reach temperatures of several thousand degrees Celsius, hotter than the outer layer of a small star. And yet, remarkably, the inside of the stone may stay cool. Rock is a poor conductor of heat. The outer skin melts, blackens, and peels away in a process called ablation. Ablation carries heat off with the falling material, almost like a shield that keeps sacrificing itself to protect what lies beneath. If the stone is large enough, only a thin outer crust ever gets hot. The heart of the rock, sometimes just a centimeter or two below the surface, might never rise above the temperature of a warm summer day. This is one of the most surprising details in the whole Panspermia question. The fireball we see streaking across the sky may look like total destruction. To anything living deep inside, it may feel like almost nothing at all. Scientists have tested this idea in careful ways. They have taken rock samples, seeded them with hardy microbes, and mounted them on the outside of returning space capsules. In some experiments, small colonies of bacteria and lichens have survived the plunge back through Earth's atmosphere while riding the outside of a spacecraft. The outer millimeters were cooked away, as expected, but sheltered pockets held on. A few living things came back down alive. Other tests suggest the opposite. Small stones, or fragile ones, or ones that tumble and expose fresh sides again and again, can be heated all the way through. Whether life survives seems to depend on size, shape, spin, angle, and the exact makeup of the rock. A stone that enters at a shallow angle skips across the upper air, like a stone skipping across a pond, losing speed slowly and staying cooler. A stone that plunges straight down suffers the full violence of the entry. So, the answer is not a simple yes or no. It is a matter of luck and geometry. There is also the landing itself. A large meteor may explode in the air, torn apart by the pressure of its own passage. A smaller one may reach the ground almost gently, slowed by drag, until it drifts down at the speed of a falling leaf. Some meteorites that lie in museums today were cool enough to touch soon after they landed. Others struck with force enough to make craters wider than cities. Between these two extremes lies a narrow window in which a passenger might step off the ship, so to speak, and find itself alive on a new shore. The mystery deepens when you consider that all of this must happen at both ends of the trip. The rock must be launched without killing what rides inside. It must endure the long, cold silence between stars. And then, at journey's end, it must survive this final trial by fire. The odds against any one stone completing all 3 stages must be small. But space is vast, and time is deep, and small odds multiplied by enormous numbers can still add up to something. Some researchers argue that the entry problem is the strictest filter of the 3. Others counter that meteorites recovered on Earth have been found with unmelted interiors, and that the survival experiments in orbit prove the principle. Both views have evidence on their side. The question of how often a rock actually delivers a living passenger, rather than a sterilized one, remains genuinely open. For now, picture the stone falling. Picture the bright streak in a sky over some ancient sea, on some world, older than ours or younger. Picture the fireball fading. Picture the warm, dark heart of the rock cracking open in a shallow pool, releasing whatever slept inside. It may have happened. It may never have happened. The universe has not yet told us which. Comets are strange, quiet things. They spend most of their lives far from the sun, drifting in the cold dark at the edge of our star system. Out there, in a wide shell of icy bodies called the Oort cloud, they move so slowly they seem almost frozen in place. A single loop around the sun can take a comet millions of years, and in all that time, the ice at its heart barely changes. That slow, cold patience is part of what makes comets interesting to people who study the question of traveling life. If a rock is a kind of ship, a comet is more like a floating pantry. It carries water, it carries carbon, it carries tiny grains of dust locked inside old ice. When scientists study comet material, they find long chains of molecules that look surprisingly close to the ones life uses. Amino acids, the small parts that build proteins, have been found in dust brought back from a comet's tail. Simple sugars have been found in meteorites that likely came from comet-like parents. None of this is life, but it is the shopping list. One idea is that comets did not carry living things to the young Earth, but instead delivered the raw parts. Every few thousand years, a comet would pass close, shedding ice and dust. Some of that material would settle gently onto our world. Over long stretches of time, This steady rain could have enriched our oceans with the building blocks that early life needed. In this view, comets are more like couriers of chemistry than couriers of biology. A different idea goes a step further. Some researchers wonder whether the interior of a comet could shelter something more than molecules. Deep inside a comet, below layers of dust and ice, the temperature stays low and steady. Radiation from space cannot easily reach the core. If a small pocket of liquid water formed there, warmed by the slow decay of radioactive grains, it might last for a long time. In such a pocket, could dormant microbes survive a journey between stars? The honest answer is that we do not know. No one has ever found a living cell inside a comet, but no one has yet ruled it out either. Against this, many researchers point out that comets are not gentle homes. Their surfaces are scoured by sunlight when they swing close to a star. Their ice sublimates, meaning it turns straight from solid to gas, blasting material outward in bright jets. Anything living on the outer crust would be lost in these outbursts, and the deeper you go, the harder it becomes to imagine how life could have gotten inside in the first place. The comet debate, in this way, is quiet and unfinished. The details found by close-up comet missions have been small but lovely. When a spacecraft landed on a comet named 67P, a few years ago, it sniffed the thin gas rising from the surface and found dozens of different molecules. Some smelled, in a chemical sense, like rotten eggs and bitter almonds. Others were softer, more sugary. The comet had a faint scent of a chemistry set left open in a cold room. Grains of dust from its surface, seen under a microscope, looked porous and fluffy, like tiny black snowflakes made of soot and ice. These are the textures scientists find beautiful. Each grain is a small time capsule from the birth of the solar system. Comets also carry heavier water. Some of the water locked in their ice contains a slightly heavier form of hydrogen, called deuterium. By measuring how much heavy water a comet holds, researchers can compare it to the water in Earth's oceans. Some comets match closely. Others do not. This mismatch is one of the small puzzles that keeps the comet delivery idea open rather than closed. Perhaps only certain comets contributed to our seas. Perhaps most of Earth's water came from a different source altogether. The question is still being weighed. For tonight, it is enough to picture a comet drifting in the deep cold. Its surface is dark, darker than coal, coated in ancient dust. Beneath the crust lies ice older than the sun's first planets. Somewhere inside, perhaps there are pockets of chemistry waiting to be understood. Whether any of that chemistry ever stirred toward life, we cannot say. Whether comets are simply groshers of the young worlds they pass, or something stranger, remains an open question. They move slowly through the dark, keeping their secrets folded inside layers of frost, willing to wait as long as it takes for someone to look a little closer. For most of human history, no one had ever seen a visitor from another star. We watched comets appear and fade. We watched meteors streak across the summer sky. But everything we tracked, every stone, every icy wanderer, belonged to our own sun. It rose from our own family of worlds, looped around our own star, and returned. The idea that a rock from another solar system might pass through ours was only a thought experiment, a soft possibility living in the pages of scientific papers. That changed on a quiet evening in October of 2017. A telescope in Hawaii called Panspermia, perched high on the volcano Haleakala, spotted something small and fast moving through the inner solar system. At first it looked like an ordinary comet or asteroid, but as astronomers tracked it night after night, the numbers refused to settle into any familiar shape. Its path was not a closed loop around the sun. It was open. It was a hyperbolic curve, meaning the object was moving too fast for the sun's gravity to hold on to it. It had come from somewhere else, and it was leaving. They named it Oumuamua, a Hawaiian word that carries the sense of a scout, a messenger reaching out from the distant past. And in every way that mattered, it was exactly that, a traveler from another star, drifting through our neighborhood after what may have been millions of years of silence between the stars. The object was strange in ways that are still debated. It appeared long and thin, tumbling end over end, though no one ever saw it as more than a point of light. Its brightness rose and fell as it turned, hinting at a shape unlike almost anything in our own solar system. It gave off no visible tail, no cloud of dust, and yet its motion showed a small extra push, as if something were gently venting from its surface. Some researchers suggested it was a fragment of a shattered planet from another star. Others thought it might be a piece of a comet stripped of its ice. A few floated more speculative ideas, including that it could be an artifact of some kind. That last suggestion remains a minority view, and most astronomers place their bets on natural explanations that we simply have not seen up close before. Then, less than 2 years later, a second visitor arrived in August of 2019. An amateur astronomer in Crimea named Gennady Borisov, working with a telescope he had built himself, noticed a faint smudge moving in a peculiar way. Follow-up observations confirmed what he suspected. This too was a stranger. This too was moving on a path that no ordinary comet from our system could follow. It came to be called Comet Borisov, or by its formal name, 2I/Borisov, the 2 marking it as the second interstellar object ever confirmed. Borisov looked much more familiar than its predecessor. It had a bright coma of gas and dust. It had a tail. In many ways it behaved like the comets we already knew, though its chemistry hinted at a slightly different birthplace. Astronomers found unusually high amounts of carbon monoxide streaming from its icy body, more than in most comets from our own solar system. It was a small clue, a whisper of a different chemistry, shaped by a different star. These 2 visitors changed something quiet but important. They proved with hard data that objects do travel between the stars. The old thought experiment became a measured reality. If 2 such objects pass through in only 2 years of careful watching, then the true number crossing our solar system at any moment must be far larger. Some estimates suggest that thousands of interstellar rocks may drift through the outer reaches of our sun's territory at any time, most of them too dark and too distant to notice. For those thinking about panspermia, this was a soft but genuine turning point. If natural stones can move from one star system to another, then in principle they could carry whatever they hold within them: ice, organic molecules, perhaps in some rare case, something more. Whether any such carrier could still hold living cells after such a long crossing is a separate and far harder question. Neither Oumuamua nor Borisov showed any sign of biology. No one claims that they did. Yet a door that had been closed for centuries had opened just a crack. We now know the Postal Service exists. We simply do not know if anything is ever mailed. The question of what these travelers might one day carry, and what earlier ones may have already brought, is one we can only sit with for now, gently, in the quiet. Now for a strange thought, one that only settled into science quite recently. Not every world in the galaxy is bound to a star. There are worlds that drift alone, moving through the dark between suns, carrying no daylight and no seasons. Astronomers call them rogue planets, or sometimes free-floating planets, and they may be more common than anyone once believed. The old picture of the galaxy was neat and orderly. Stars sat in place, planets circled them, and the space between was mostly empty. That picture is slowly changing. Surveys that watch for tiny flickers of distant starlight have found signs of many unbound worlds, some as large as Jupiter, some perhaps closer in size to Earth. How many drift out there is still an open question. Some estimates suggest there could be more rogue planets in our galaxy than there are stars. Others suggest the number is far smaller. The truth may sit somewhere in between. For our sleepy question about traveling life, rogue planets add a strange new layer. A rocky world without a sun sounds like the coldest, deadest place imaginable. And on the surface, it would be. Without sunlight, the air would freeze and fall as snow. The ground would harden to something like stone glass. Yet some researchers wonder if the interior of such a world might still be warm. Heat from the slow decay of natural elements in the rock could linger for billions of years. A thick atmosphere of hydrogen, if the planet held onto one, could act like a heavy blanket deep beneath a frozen crust. A hidden ocean might survive. If that is true, and it remains an if, then a wandering world could carry liquid water through the space between stars. It would not need a sun. It would need only its own inner heat and a good coat of ice to seal that heat inside. Such a world would be its own tiny biosphere, sailing quietly through the dark for stretches of time we can barely picture. Any life within it would never see stars. It would live in warm blackness, tucked under kilometers of ice, unaware that its whole world was moving. The competing view is more sober. Many researchers point out that we have not found direct evidence of any such subsurface ocean on a rogue planet. We have only models, and models are only as good as the assumptions inside them. A rogue world might lose its atmosphere quickly. Its inner heat might drain away faster than we hope. Its ice shell might be too thick to allow any interesting chemistry near the surface, and too thin to protect any liquid below. Both pictures fit what little data we have. Still, the thought is a soft one to hold as you rest. Imagine a dark planet the size of Earth, moving through interstellar space at tens of thousands of kilometers per hour. On its surface, nothing but silence and frost. Below the surface, perhaps, a slow, warm sea. And perhaps, in that sea, something drifting that we would recognize as alive. The world would not know where it was going. Neither would its passengers. There is one more surprise here. If rogue planets carry hidden oceans, they might also carry them into other star systems. A wandering world does not usually get captured by a new sun, but it can pass close. It can brush through the outer edges of another system, feel the tug of that system's gravity, and shed material. Ice, dust, small fragments. Some of that material could fall inward toward the new sun's warmth. What began as a frozen passenger on a lonely world might, in some rare case, end its trip in a warmer place. Whether any life could still be tucked inside such a fragment after such a long, cold journey is completely unknown. The idea flips the usual picture on its head. In the standard version of Panspermia, life travels as tiny hitchhikers on small rocks. In this stranger version, life could travel as an entire hidden ecosystem inside a planet-sized ark. The ark carries its own heat, its own water, its own shielding. It needs no sun for the trip. It only needs to eventually meet one, or to shed some of itself in passing. Whether any rogue world actually holds such an ocean, we do not know. Whether life could begin in such isolation, we do not know. Whether such a world could truly seed another system, we do not know. What we do know is that the galaxy contains far more strange, dark, drifting things than the old map suggested. The space between the stars is not as empty as it looks. It may be quietly full of wandering worlds, each keeping its own secrets in the cold. Stars are almost never born alone. They form in vast clouds of gas and dust, and when one part of that cloud collapses under its own weight, it usually does so in the company of many siblings. These nurseries can hold hundreds or thousands of young stars, packed together far more tightly than the stars we see in the night sky today. For a stretch of time, measured in millions of years, these young suns drift near one another, close enough that their planetary systems may brush against each other's gravity. This closeness matters for the question we have been sitting with. If life can ride on rocks between worlds, the odds of that ride reaching another star system depend on how far the rock has to travel and how long it has to survive. In our current neighborhood, the nearest star sits about 4 light-years away. That is a vast distance, and a rock tossed from Earth at ordinary escape speeds would take many millions of years to arrive. But in a young star cluster, the neighbors are far closer. Some models suggest the stars in a birth cluster may pass within a few hundred astronomical units of each other, sometimes less. A stone flung from one young planet could reach a neighbor's outer edge in a much shorter window. This shifts the whole picture. The mystery of interstellar seeding becomes less about lonely rocks crossing endless dark, and more about crowded nurseries, where debris from one forming world might rain into the neighborhood of another. Some researchers wonder if the earliest solar systems traded material regularly, like children swapping stones in a schoolyard. If any of those stones carried simple microbes, or even the chemical scaffolding for life, then whole clusters of young stars could have shared a common seeding. There is a competing view worth holding beside this one. Even in a crowded nursery, most of the ejected debris would still miss any planet. The volume of space, even at close quarters, is enormous compared to the size of a world, and the young planets themselves would be hot, half molten, or still gathering their atmospheres. A rock arriving too early might land on a surface too hostile to hold on to any passenger. So, while proximity helps, it does not guarantee the trade. The question of whether nurseries actually pass life around or merely swap sterile debris remains open. Astronomers have found young clusters throughout the galaxy that let them study this idea from a distance. Soft glowing regions of pink and blue gas cradle, newborn suns still wrapped in dusty disks inside. Those disks, the first pebbles clump into boulders, and boulders into planetesimals. Collisions among these bodies are common. Each impact throws material outward, and in the tight quarters of a nursery, some of that material can drift into a neighbor's disk. In this way, the raw ingredients of planets may already be shared across many young stars before the stars ever go their separate ways. Our own sun is thought to have been born in such a cluster. The evidence lies in tiny clues within old meteorites, in traces of elements that could only have formed inside a nearby dying star. That neighbor must have been close enough to sprinkle its ashes into our forming disk. If that kind of exchange happened with heavy elements, some scientists ask whether it might also have happened with more delicate cargo, including organic molecules, or perhaps something more. The nursery period does not last forever. Over tens of millions of years, the stars in a cluster drift apart, pulled by the tides of the galaxy and by their own motion. The sun's siblings scattered across the Milky Way long ago, and we can no longer point to them with certainty yet. If any of those siblings received or gave a biological gift during the crowded years, that gift could now be spread across hundreds of worlds we cannot identify. Whole family trees of biospheres might exist without knowing their shared beginning. This is the symphony hidden in the Panspermia question. It is not only about single rocks on single journeys, it is about how stars are born together, how disks touch and mingle, how young systems share their debris, and how the earliest chapters of every planet may be written in the same crowded room. Whether life truly rode along in that room remains one of the deepest open questions in astronomy. The physics allows it. The geometry favors it. The evidence for or against it lies scattered across a galaxy we can barely reach. And so the wandering continues, quietly patient as the drifting stars themselves. The sun we see today drifts alone through its arm of the galaxy. Its nearest stellar neighbor sits more than 4 light-years away, a distance so vast that even light takes years to cross it. But it was not always this way. The sun, like nearly every star we can see, was born inside a crowded stellar nursery, and that early crowd may matter more to our story than almost anything else. When a giant cloud of gas and dust collapses to make stars, it rarely makes just one. It makes hundreds, sometimes thousands, packed together in a loose cluster. These young stars share the same cloud, the same chemistry, the same slow spin of dust and ice. For a while, they live close enough that their outer edges brush against each other. Some researchers estimate that the sun's siblings once sat only a few tenths of a light-year away. That is close enough that a rock flung from one system could reach another in a human lifetime, or a few of them. This changes the panspermia question in a quiet but powerful way. Across the vast, empty galaxy today, the odds of a rock finding another star seem tiny. But in a young cluster, the odds grow much larger. A single impact on a young world could send debris drifting into the space between siblings. Some of that debris might fall, over time, onto planets forming around neighboring stars, if any of it carried living cells, or even the delicate chemistry that leads to life. The whole cluster could have shared a common seed. We do not know if this happened, but the setting was right. The sun was probably born in a cluster of a few hundred to a few thousand stars. Those siblings have long since scattered, pulled apart by the slow tides of the galaxy. They now drift among the other stars, unmarked and unknown. Some astronomers search for them by looking for stars with the same chemical fingerprint as the sun. A handful of possible matches have been suggested, though none confirmed with certainty. The sun's family has become anonymous. There is a competing view worth sitting with. Even in a crowded cluster, the total mass of ejected rock is small, and most of it never intersects another world. The odds might still be low. And even if a rock arrives, the receiving planet has to be ready. It needs liquid water, a stable surface, a chemistry that welcomes the traveler. Timing matters as much as distance. A rock arriving 100 million years too early lands on molten rock. A rock arriving too late finds a world already claimed by its own biology, if any biology exists. Some researchers think the window is narrow enough to make cluster panspermia rare, even under ideal conditions. Still, the picture is striking. Picture the sun as a young star, its planets still forming, its outer edges glowing with warm dust. Around it, dozens of sibling stars glow too, each with its own disk of gas and rock, each shedding small fragments as its worlds take shape. The space between them is not empty yet. It is full of slow-moving debris, drifting from one system to another, a shared cloud of building material. If life had already begun on any one of those worlds, it might have spread quietly to the others, carried inside stones no larger than a fist. Time changes everything. The cluster loosened, the stars drifted, the sun found itself alone, and its siblings became strangers. The bridges between systems if any existed, closed. What we see now is the aftermath, long after the crowded chapter ended. And so the question of shared origins may be a question we cannot answer by looking at today's sky. The evidence, if it exists, would have to be found in the DNA of living things, or in the chemistry of ancient meteorites, or in the atmospheres of planets around stars that once shared the sun's cradle. Some astronomers dream of finding one of those long-lost siblings and studying its planets. If a world there shared any biological signature with Earth, a case for cluster panspermia would grow much stronger. If those worlds showed completely different chemistry, the case would weaken. For now, we do not have that data. The siblings remain hidden in the crowd of the galaxy, and their planets remain far beyond our reach. What we can say is that the setting for panspermia was at least once much friendlier than it is today. The galaxy has grown wider and lonelier since. Whether life used those early bridges, or whether each world lit its own small flame in isolation, is a question the sky has not yet answered. Long before any rock could carry a passenger between the stars, the space between them was already busy with chemistry. Astronomers point their telescopes at cold, dark clouds of gas and dust and find something strange in the light. The clouds are not empty. They hum with molecules, some simple, some surprisingly rich, and each one leaves a fingerprint in the colors of the light passing through. The way we learn this is quiet and patient. Light from a distant star travels for centuries and passes through a drifting cloud on its way to our telescopes. Along the way, certain molecules in the cloud drink in specific colors of that light. When we spread the starlight into a rainbow, we see thin dark lines where those colors are missing. Each missing color is a signature, a note in a chemical song. From these fingerprints, we have found water, ammonia, methanol, and the sugar-like molecule glycolaldehyde, floating in clouds where new stars will one day form. The colors of these clouds are worth pausing on. Some glow faintly red, lit from within by young stars pushing on the hydrogen around them. Others shine in soft green when carbon molecules catch a passing wave of ultraviolet light. Many are simply dark, blocking the stars behind them like ink poured across a page. Within that ink lie grains of dust, no larger than smoke particles, coated in thin films of ice. On the surfaces of those icy grains, atoms meet and combine in the deep cold, patient in a way nothing on Earth could match. That patience matters for our question. If the ingredients of life were only made on planets, then every world would have to build them from scratch. What the light of these dark clouds suggests is different. The building blocks appear to be everywhere, spread through the galaxy like flour dusted across a table. Amino acids, the small units that make proteins, have been found inside meteorites that fell to Earth. Some of those meteorites carry the same amino acids used by living things, and some carry versions life never uses. The mixture is broader than biology and older. One idea, then, is that panspermia may not even be the main event. Perhaps the true story is a slow, steady rain of chemistry from the clouds themselves onto every young world. Rocks arriving from other stars would be only the final touch, adding whole cells to a soup already thick with the right molecules. In this view, life does not need to hitch a ride. The ride happens at the molecular level, quietly, over billions of years. A competing view holds that raw ingredients are not enough. A pile of amino acids is not a living thing, any more than a heap of bricks is a cathedral. Something must arrange them, fold them, teach them to copy themselves. That leap from chemistry to biology may be so rare that it happens once in a galaxy, or once in many. If that is true, then rocks carrying real, living cells would matter enormously. They would be the seed, and the interstellar chemistry would be only the fertile ground waiting for it. The light gives hints, but no final answer. In the glowing bands of a nebula, we see the colors of hydrogen, oxygen, and sulfur painted across light years. In the darker filaments, we sense the presence of complex carbon rings called polycyclic aromatic hydrocarbons, which drift through much of the galaxy. These molecules resemble sooty fragments from a candle flame, only they float in interstellar cold and glow faintly under ultraviolet stars. Some researchers wonder whether these carbon rings could serve as scaffolding for the earliest steps toward biology. Others suggest they are simply cosmic exhaust, a byproduct of dying stars with no special role to play. What remains open is the boundary between chemistry and life. We can watch a cloud brew sugars in the dark. We can find amino acids inside stones. We can even see, in some comets, the glycine that living cells use every day. But nowhere in the sky has anyone yet caught the moment when this quiet chemistry stirs, folds, and begins to copy itself. That threshold is the great unknown, and until it is crossed in a laboratory or spotted in a distant world, we cannot say whether life needs a traveling seed or grows freely from what the light already reveals. For tonight, it is enough to picture those cold clouds glowing softly between the stars. Inside them, molecules that share our own chemistry drift and wait, patient beyond any human clock, holding a question we have not yet learned how to ask. So far we have wondered whether life might have arrived on Earth from somewhere else. Tonight, let us gently turn that question around. If rocks can leave Mars and land here, then rocks can also leave Earth and land somewhere else. Every large impact that has ever struck our world has sent some fraction of our surface upward into the black, and some of those fragments, over billions of years, may have carried more than dust. The sound of this idea, if we could hear it, would begin as a deep rumble. Picture the low tremor of a great impact, felt through the bones of the crust. Instruments on Earth turn seismic waves into slow, groaning tones. When a mountain-sized object strikes, that groan becomes something closer to a bell rung once and left to fade for hours. The ground itself sings, and in that ringing moment, tiny pieces of the planet leap into the sky. Most of that material falls back down, but a small share moves fast enough to escape entirely. Once free, it drifts in silence. If a microbe were riding along, it would hear nothing at all, only the soft hiss of solar wind, which scientists have translated into eerie whistles and low static using radio instruments on spacecraft. That sound, converted from plasma vibrations, is the closest thing to a lullaby the outer solar system offers. The question is whether any of those departing Earth rocks could have reached another world with life still clinging to them. Some researchers have run the numbers and found the answer is not obviously no. Simulations suggest that pieces of Earth, thrown up by the largest impacts in our planet's history, could in principle reach the moons of Jupiter or Saturn, or even drift into the outer edges of the solar system. A few might, over immense stretches of time, wander farther still. One possibility is that Earth has been quietly seeding its own neighborhood for billions of years. Under this view, if we ever find microbes on Europa or Enceladus, we should first ask whether they might be distant cousins of our own bacteria, carried out on ancient debris. That would be a strange kind of discovery. Not alien life, but familiar life in a very unfamiliar place. A competing view holds that this is far too optimistic. The odds of a rock leaving Earth, surviving in space for the right length of time, and then landing gently enough on a habitable surface are extremely small. Multiply those small odds together, and the chance of successful seeding becomes very faint. In that view, Earth's material may indeed be scattered through the solar system, but the living passengers almost certainly did not make it. The rocks arrived, the microbes did not. Between those two views sits a quieter middle idea. Perhaps a handful of transfers did succeed, but only to nearby worlds, and only during the earliest, most violent chapter of the solar system, when impacts were frequent and orbits were still settling. If that is true, then any shared biology would be ancient, buried deep and hard to find. It might take drilling through kilometers of ice on a distant moon just to reach the evidence, if the evidence exists at all. The sound of that search, in its own way, is the hum of a drill. Engineers, testing ice-penetrating tools, record the low grind of blades biting into frozen samples. It is a patient sound, a sound of very slow progress. Any answer about Earth-seeded life on other moons is likely to come, if it comes at all, from machines whistling and grinding through ice under skies we will never stand beneath ourselves. There is one more layer to sit with. Even if Earth has sent living things outward, we may never be able to prove it. A microbe found on Europa might share our genetic code because it came from us, or because life everywhere uses the same code, or because our own life came from the same distant source as theirs. Three very different stories could leave the same fingerprint. Untangling them may be beyond the reach of any single mission or any single generation of scientists. For now, the idea rests as a soft possibility. Every asteroid strike in our deep past may have been a whisper sent outward. Some of those whispers may have landed on frozen worlds and found nothing to greet them. Some may have landed and died quickly, and a very few, in the gentlest imaginable version of the story, may have found a warm crack in the ice and settled in and begun a slow life of their own, entirely unaware of the blue planet that had, long ago, thrown them into the dark. There is a small puzzle at the heart of our own story, and it hides inside the numbers. Earth formed about 4.5 billion years ago. For its first few 100 million years, the surface was a place of molten rock, endless impacts, and boiling seas. Not a gentle nursery. And yet, when we look at the oldest rocks that still hold a record of the past, we find hints of life reaching back nearly 4 billion years. That leaves a window that feels, to some researchers, surprisingly short. The math is simple, and that is part of its quiet beauty. Take the age of the Earth, subtract the age of the earliest possible fossils. What remains is the time life had to appear. Some estimates give it a few 100 million years, others a bit more. In the deep clock of the universe, that is a brisk pace, a blink, almost, compared to the ages of stars. This is where the puzzle begins. If life needed only a short stretch to arise here, and either the recipe is easy, or something helped it along, both answers are worth sitting with, and neither is settled. One idea is that life is simply quick to start, whenever the conditions are right. Warm water, gentle chemistry, a few billion years of patient shuffling among the right molecules, and biology begins on its own. In this view, the short window is not a mystery at all. It is a hint that the universe is friendly to living things, and that many worlds should carry their own quiet beginnings. Some researchers find this elegant. Life as a natural consequence of chemistry, given time and a warm sea. Another view looks at that same short window and wonders if life is so easy to make. Then repeated experiments in the lab should have shown it by now, at least in simple form. So far, they have not. The steps from raw chemistry to a living cell remain hidden. If those steps are rare, then a few 100 million years may not be enough. And that is where the traveling stones come back into the picture. If life did not begin here, but arrived here, then the clock changes. The real starting point could be far older. On some other world, in some other sea, Earth would then be a second home rather than a first cradle. The short window would not need to hold the whole miracle. It would only need to hold the arrival, the landing, and the taking route. The numbers here are gentler than they seem. A microbe, tucked deep inside a rock, drifting through cold space, could sleep for millions of years. Some estimates suggest that a fair fraction of material blasted off one young planet could reach another within a single solar system in less than 1 million years between stars. The trip stretches far longer, into tens or hundreds of millions of years long, but not impossible, against the age of the galaxy, which is more than 10 billion years old. Set those two clocks side by side. The galaxy is old. Life, once it exists somewhere, has time to spread. If even a small trickle of living rocks crosses between star systems in each billion years, the sum grows, one seeding here, one seeding there, quietly compounding across the long ages. The math does not prove it happened. It only shows that it is not forbidden. There is a competing thought, and it deserves its place. Perhaps the short window on Earth is a trick of preservation. The oldest rocks are rare and battered. Signs of life within them are faint, and often argued over. If the earliest evidence is misread, then life may have taken far longer to arise than we now think. The window could be wider, the mystery softer, and no traveler from another star would be needed to explain it. Both possibilities live inside the same numbers. Chemistry that works quickly, or a slow beginning we cannot yet see, or a seed carried in from elsewhere. Each answer reshapes the meaning of the count. What makes this puzzle beautiful is that it rests on such simple arithmetic. Subtract one age from another. Compare the result to the ages of stars. Notice what fits and what strains. The universe, in its grand shape, seems to run on modest sums, orbits that keep their promises, light that travels at one steady speed, rocks that fall in predictable arcs. And within those tidy rules, a question hangs, unanswered. Did life here begin here, or did it begin somewhere else, in a time and a sea we will never see, and simply arrive when the young Earth had cooled enough to hold it? The numbers allow both. The numbers for now do not choose. Picture a small icy moon, far from any warm sun, drifting in the shadow of a large planet. Its surface is cracked and pale, patterned with fine ridges that catch the faint starlight. Beneath that shell of ice, some researchers suspect a hidden ocean rolls in slow, dark currents. Now imagine a small rock falling from the sky. It has traveled for millions of years, and this moon, this quiet frozen world, might be the place it finally lands. For Panspermia to work as more than a fragile dream, a traveling rock must not only survive the trip, it must also arrive somewhere gentle enough to matter. That last step is where the whole idea grows delicate. A rock could carry sleeping microbes across the emptiness for ages, only to strike a molten surface, or a world without water, or a place where the air burns everything to ash. On the way down, the catching is as hard as the throwing. Think of how narrow the window truly is. A world must have liquid water somewhere, at least in patches or hidden layers. It must have a stable temperature, or at least a stable range. It must have some shield against harsh radiation, whether an atmosphere, a magnetic field, or the sheer thickness of ice above a buried sea. and the rock itself must slow down enough that the microbes inside are not cooked or crushed on arrival. Each of these conditions is thin. Together, they seem almost impossibly thin. Earth itself is a strange piece of good fortune. Our planet sits in a narrow band where water can be liquid, not frozen, not boiled. Our atmosphere is thick enough to burn away small stones and slow down bigger ones, but thin enough to let sunlight reach the ground. Our magnetic field turns aside the worst of the sun's storms. Move Earth a little closer to the sun, and the oceans might have boiled long ago. Move it a little farther, and they might have frozen solid. It is a fragile balance, and we do not fully understand how many worlds achieve it. Some researchers wonder whether small moons might be better catchers than planets. A moon with a thick, icy crust could absorb an incoming rock softly, the way snow catches a falling stone. If there is liquid water beneath, the melted channel from the impact might slowly reach that hidden sea. In this picture, a moon like Europa or Enceladus becomes a kind of gentle net, quietly gathering whatever the galaxy sends its way. One idea is that such moons could hold the record of many arrivals, layer upon layer, over billions of years. Others push back on this. A rock arriving at high speed still carries enormous energy. The heat of impact could sterilize whatever it was trying to deliver. And even if microbes survived the crash, they would then face a strange new chemistry, an alien salt balance, pressures far beyond their old home. The question of whether any traveler could truly wake up and settle in remains open. Surviving the trip is one puzzle. Fitting into a new world is another. We do not know whether the icy shell above them is a barrier or a slow cycling conveyor. Small changes in these numbers could mean the difference between a welcoming cradle and a sealed tomb. Even our best instruments only guess at what waits beneath that pale crust. There is a quieter thought here too. If catching a rock is this hard, then perhaps every living world we ever find is a small miracle. Perhaps biospheres are like candles in a vast dark room, each one flickering because 1,000 small conditions happened to align. Some researchers find this comforting, others find it lonely. Both feelings may be honest responses to the same set of unknowns. And yet, the galaxy has had a very long time, billions of years, countless collisions, countless ejected stones, countless moons drifting past. Even a rare event, given enough time, can happen more than once. Whether that has been enough to link worlds together, or whether each biosphere has simply grown up alone, is a question the evidence has not yet settled. The fragile balance is real. The chances are small, but small is not the same as impossible. And the sky is patient in a way we can barely imagine. So the traveling rock and the waiting moon remain suspended in that quiet uncertainty, still passing one another in the dark. If life truly rides between the stars, we should be able to find its fingerprints somewhere in the sky. That is the quiet hope guiding one of the strangest searches in modern science. Somewhere out there, in the dust of a comet or the ice of a distant moon, there might be a molecule that does not match anything on Earth. Or, stranger still, one that matches too well. Both outcomes would tell us something profound. And yet, so far, we have found neither. The trouble is that we barely know what we are looking for on Earth. Life uses a very particular chemistry. It prefers certain versions of molecules over their mirror images. It builds proteins from a small set of amino acids and stores information in the twisting rungs of DNA. If we found the same pattern on Mars or Europa, we would face a puzzle. It could mean life sprang up twice in nearly the same way. It could also mean that both worlds share a single origin, carried between them on ancient stones. Some researchers wonder if we might already have samples of foreign biology sitting in freezers waiting to be recognized. Meteorites collected from Antarctic ice sometimes carry organic molecules. A few, over the decades, have shown tiny shapes that look faintly like fossil microbes. The most famous of these is a Martian rock called ALH84001, found in the ice fields in 1984. Some scientists argued its microscopic tubes were traces of ancient Martian life. Others argued they formed through ordinary chemistry, no biology needed. The debate has never fully settled. The rock sits in a clean laboratory, still holding its secret. There is another approach, one that reaches further out. Robotic landers on Mars scoop soil and sniff for the gases that living things tend to make. Methane, in particular, comes and goes in the Martian air in ways no one has fully explained. One idea is that microbes hidden underground release it in slow breaths. Another is that simple rock chemistry produces it as water seeps through mineral cracks. Both are possible. Neither has been proven. The mystery hangs in the thin red air, waiting for a better instrument or a lucky drill. Farther still, our telescopes turn toward the atmospheres of planets around other stars. When such a world passes in front of its sun, a sliver of starlight filters through its air. Hidden in that light are the signatures of gases. Some combinations, like oxygen mixed with methane, are hard to explain without living things constantly refreshing them. If we ever saw such a mixture on a distant world, it would raise the Panspermia question in a new form. Would that life share our chemistry, or use something wholly different? A shared chemistry might hint at rocks passing between systems long ago. A different chemistry would suggest that life invents itself again and again, wherever conditions allow. The instruments are still too young to give clear answers. Even our best telescopes catch only faint whispers from these far atmospheres. Clouds confuse the signal. Stars flicker in ways that mimic the marks of gases. Every claimed detection so far has come with careful footnotes and gentle disagreements between teams. Nothing has crossed the line from interesting hint to solid proof. That line, when it is finally crossed, will be one of the quietest revolutions in human history. Closer to home, missions to icy moons carry the same hopes. In smaller vessels, Europa hides an ocean beneath its shell of ice. Enceladus sprays plumes of water into space through cracks near its south pole. Future probes could fly through those plumes and taste them, looking for the molecules of life. If they find something, the next question will be whether it looks like us or looks like a stranger. A stranger would be thrilling. A cousin would be even more so, because a cousin would mean the seeds of life have traveled farther than we ever imagined. For now, the search continues without answers. Laboratories run experiments on tiny microbes to see how long they can sleep in cold vacuum. Astronomers scan interstellar visitors for chemical clues as they streak through our system. Chemists tease apart meteorite dust, one grain at a time. Each effort is a small candle held up in a vast dark room. None of them has yet lit the whole space, but each one pushes the shadow back a little further. The question of foreign biology stays open, and that openness is itself a gift. It means the sky still holds a secret worth chasing. It means the story of life is not finished, and the next chapter might arrive on a passing stone, a scoop of ice, or a shimmer of light from a world we cannot yet name. Somewhere out there, on some quiet moon or warm ocean world, life may already be starting again for the first time. Not our life, not our chemistry, a second genesis, a separate spark, lit from different ingredients, following different rules. If we ever found such a thing, it would change everything we think we know about the living universe. And yet we would only know it was truly separate if it looked nothing like us at all. That is the puzzle of a second genesis. If life spread between the stars on rocks and dust, then finding new microbes on Mars or Europa might not tell us what we hope. They might share our chemistry because we share a source. Same code, same building blocks, same distant ancestor drifting frozen through the dark. To prove a second genesis, we would need to find something so different that no shared parent could explain it. A different set of letters in the genetic alphabet, a different handedness to its molecules, a whole new tree of life rooted in some other soil. Some researchers call this shadow biosphere thinking, the idea that even here on Earth, in the corners we have not searched, a second kind of life might already exist, microbes built on other chemistry, hiding in hot springs or salt lakes, quietly living beside us without ever being noticed. So far, no clear sign has turned up, but the search itself is young. Our tools are tuned to find life like our own. A different kind of life might slip right through them, unseen. Now imagine the far future, 1,000,000 years from now, 1,000,000,000. The sun will slowly grow brighter and hotter. In about 1,000,000,000 years, its warmth may push Earth's oceans into a slow simmer. Life as we know it will retreat or change or end. Farther out, worlds that are frozen today might thaw. Europa's icy shell could soften. Titan's methane seas could stir. If life is waiting under those crusts, its long winter might finally break, and the question of whether it came from us, or from somewhere else, or from nowhere at all, would still be waiting to be asked. Deeper into the future, the sun will swell into a red giant. It will swallow Mercury, then Venus, and reshape the inner solar system into something unrecognizable. Rocks will melt, atmospheres will boil away, yet some material will scatter outward, flung into space by the dying star's own breath. If any spores or sleeping cells still lie tucked inside deep rocks, they might ride that scattering outward. Into the wider galaxy, our world would then become, in its final act, a seed pod, the same trick that other worlds may have played on us long ago. Farther still, the stars themselves will change. New suns will keep forming for tens of billions of years, born from the clouds of gas that older stars left behind. Some of those new suns will pull together new planets, and those planets will inherit the chemistry of everything that came before them, including perhaps the shattered remains of long-dead biospheres. One idea is that this slow recycling could keep the thread of life running through cosmic time, patched together across many worlds. A competing view is that each biosphere is a fresh start, and that whatever traveled between the stars was only the ingredients, never the living cells themselves. Both remain open. A second genesis, if we ever confirmed one, would tell us that life is easy, that the universe wants to bloom, and does so wherever the water and warmth allow. But if every world we visit turns out to share our chemistry, that would hint at something else. It would suggest that life is rare, and that its spread depends on a slow, patient scattering of stones. Neither answer is proven. Neither can be ruled out with what we know today. There is something quietly beautiful in this uncertainty. Whether life is a common flame lit many times, or a single ember carried by the wind, the outcome fills the same dark sky. Worlds turning, oceans breathing, cells dividing under strange suns. The far future does not care which story is true. It only keeps unfolding, one small chemistry lesson at a time, across timescales longer than any mind can hold. For now, we sit inside a single chapter of that story. We do not know if we are the first page or the 10,000th. We do not know if any other page has ever been written. We can only look outward and inward and keep gently asking. The universe is patient. It has been becoming something new for a very long time, and it will keep becoming something new long after we are gone. Step back with me now, all the way back, until the solar system itself becomes a single warm point of light. Then further still, until our galaxy is only a soft spiral among billions of others. From that quiet distance, the question we have been sitting with tonight takes on a different shape. It is no longer only about rocks and microbes. It is about how life fits into the long story of everything. The atoms in your body were made in stars. The iron in your blood, the calcium in your bones, the oxygen in every breath. All of it was forged in the hearts of stars that lived and died long before the sun was born. When those old stars ended, they scattered their materials into space. Clouds gathered, new stars formed, planets cooled, and somewhere in that slow reshuffling, the atoms that would become you began their journey toward this moment. So, in the plainest sense, we already know that matter travels between stars. Every carbon atom in your fingertips has crossed unimaginable distances. The only open question is whether the arrangement of those atoms, the delicate pattern we call life, can survive the crossing too. That is the mystery we may never fully close. There are limits to what we can ever learn, even if we search 1,000 nearby worlds, even if we find microbes in the ice of a distant moon. We may never know for certain whether life began there or drifted in from somewhere else. The evidence would be faint. Any traveling seed would carry only the ghost of its origin. Genes change. Chemistry shifts. Over billions of years, a shared ancestry could blur into something unreadable. And there are limits of distance. The galaxy is wide, and the space between galaxies is wider still. Even if life spreads easily between neighboring stars, we may find no way to trace it back to a first spark. The trail simply grows too cold. Some researchers wonder if the origin of life is a question that has no findable answer, only better and better guesses. Yet the not knowing has its own kind of beauty. To sit with an open question for a while is not a failure. It is a form of company. People have looked up at the same stars for tens of thousands of years and wondered the same thing in different words. We are only the latest to ask. Others will ask after us with better tools and stranger ideas, and they too may end their nights uncertain. One view holds that life is rare, a quiet accident that happened once and spread slowly through the dark. Another view holds that life is common, sparking again and again on any world that offers it warmth and water. Between these two possibilities lies a whole range of gentler ideas. That life is uncommon but connected. That many worlds carry cousins of a single ancient chemistry. That the galaxy is not empty, but is not crowded either. We do not yet know which picture is closest to the truth. Perhaps none of them are. What we do know is that we belong here. Whatever path life took to arrive on Earth, it arrived. The rain fell, the oceans warmed. Something began to copy itself. From that first small trick, everything followed. The coral reefs, the redwood forests, the whales in the deep, the person listening now in a dark room. We are one of the outcomes of a process we still do not understand. If life truly does ride on rocks between stars, then we are part of a wider family than we can see. Somewhere out there, other outcomes may be unfolding. Other oceans, other forests of a kind we cannot picture, other minds looking up at their own night sky and asking the same soft question we are asking tonight, whether they exist or not. The thought itself is a gentle one. It costs nothing to imagine them, and it makes the sky feel less lonely. And if life instead began separately on Earth, alone and unrepeated, then we are something even rarer, a single flame in an immense dark room, tending itself. Either answer is a kind of miracle, either answer is worth resting with. The universe does not owe us its secrets. It only offers them slowly, in fragments, over many lifetimes. Tonight we have gathered a few of those fragments and turned them over in our hands. We have not solved anything. We were never meant to. We were only meant to look and to wonder and to feel the quiet weight of a question that is bigger than we are. And so we come to the end of our long, slow walk through this strange and beautiful question. We have followed rocks as they left their home worlds and drifted through the black. We have watched tiny microbes sleep inside stone for ages we can barely imagine. We have looked out at comets and wandering worlds, at nurseries of young stars packed close together, at visitors from other suns that passed through our sky and moved on. And in all of it, the same quiet question kept returning. Does life begin over and over on each world, alone, or does it travel, one rocky seed at a time, between the stars? We still do not know. That is the honest and lovely truth. Some researchers lean toward the idea that life is common and independent, blooming wherever the conditions allow. Others wonder if biology is rare, and if the worlds that carry it are quietly linked, cousins in a scattered family, sharing a single deep root that reaches back to a place we may never find. Both pictures are beautiful. Both remain open, and tonight you do not have to choose between them. For now, let the images settle in your mind like snow. Picture a small blue planet, wrapped in soft cloud, turning slowly against a sea of stars. Its oceans are calm, its night side glimmers with the faint gold of coastal cities. Somewhere far below the waves, in dark warm water near a vent on the seafloor, life goes about its patient work, as it has for billions of years. Whether it began here or arrived here, it is home now. Let your thoughts drift outward. See the moon above that ocean, pale and steady, holding the tides in a slow rhythm. See the pale ring of dust that circles our sun, and the outer worlds beyond, wearing their bands of cloud and their wings of ice. See the long dark road that leads out past the last of the planets, past the comets in their distant shell, into the great quiet between suns. There, in that quiet, the stones may still be traveling, small, cold, unhurried. Some of them empty, some of them perhaps carrying something asleep. They do not know where they are going. They do not need to know. The galaxy turns around them, slow as a wheel of milk and light, and they turn with it, patient beyond any human sense of patience. Picture the galaxy itself now, seen from far above. A soft spiral, its arms trailing like smoke, freckled with the pinks and blues of star-forming clouds. Billions of suns, each with its own quiet story, some of them young and bright and restless, some of them old and steady. Around many of them, worlds we have never seen, oceans we will never swim in, skies whose colors we will never learn. And drifting between all of them, the slow traffic of stones and dust and ice, carrying who knows what. You are a small, warm thing on one of those worlds. Your breath is soft, your body is heavy against the bed. The room around you is dark and safe. The universe is enormous, and it is gentle tonight. it has room for you. It has room for the question too, unanswered, held carefully, waiting for another generation to look again. Maybe one day, a probe will land on a distant moon and find a microbe that shares our chemistry. And we will know. Maybe one day we will find a microbe that does not share our chemistry at all, and we will know something even stranger. Maybe the answer will come in your lifetime. Maybe it will come long after. It is not for tonight to decide. Tonight is only for drifting, for letting the mind grow soft, for picturing the little stones out there in the dark, tumbling slowly, going nowhere in particular, taking as long as they need, for imagining that somewhere on a world you will never visit, a small tide is rolling in under two moons, and something in the water is beginning to stir, and the question of where it came from is a question they too are only beginning to ask. Rest now. The stars will keep turning without you needing to watch. The stones will keep drifting. The mystery will keep waiting, kind and patient, until we are ready to know more. You have wondered enough for one night. You have carried the question far. Let it go. Let yourself sink. Let the galaxy hold you as it has always held everything, softly, in the dark. Subscribe for a brand new space topic every night. One tap and something incredible is waiting for you tomorrow. Sweet dreams.